Welcome to the video. Today we're talking about every single type of star. Watch to the end to learn about Thorne-Zitko objects, Methuselah stars, and fuzzballs. Let's start with exotic stars. Exotic stars are composed of exotic matter, which is matter that does not consist of the usual particles such as electrons, protons, neutrons, or muons. Exotic matter is thought to be able to resist the force of gravity through a variety of quantum properties, such as degeneracy pressure or negative pressure. A quark star forms when neutrons break down into their constituent up and down quarks due to intense gravitational pressure. It is believed to be smaller and denser than a neutron star and can exist indefinitely if no extra mass is added. Essentially, it is a large, single hadron. If it contains strange matter, it is called a strange star. An electroweak star is prevented from collapsing due to radiation pressure generated by electroweak burning. This occurs in a small volume at the star's core, about the size of an apple and containing approximately 2 Earth masses. The formation of an electroweak star is thought to occur after a supernova collapse, when the gravitational attraction is too strong for quark degeneracy pressure to withstand, but can still be resisted by electroweak burning radiation pressure. These stars are denser than quark stars and can persist for up to 10 million years. A Planck star is in loop quantum gravity that can form when the energy density of a collapsing star reaches the Planck energy density. When this happens, a repulsive force emerges from the Heisenberg uncertainty principle. As gravity and spacetime are quantized, the mass energy inside the Planck star cannot collapse beyond this limit to create a gravitational singularity without violating the uncertainty principle for spacetime. A boson star is made up of bosons, which are particles with self-repulsive interaction. They are theorized to be invisible and transparent, with immense gravity that can bend light around them. They may be detectable by gravitational radiation emitted by a pair of co-orbiting boson stars. Boson stars have also been proposed as candidate dark matter objects and may have formed through gravitational collapse during the primordial stages of the Big Bang. Boson stars composed of elementary particles with spin 1 are called protostars. A preon star is a dense star made of subatomic particles called preons. They may be denser than quark stars and smaller than white dwarfs and neutron stars. Preon stars could be detected through gravitational lensing of gamma rays and are a candidate for dark matter. Alright, let's get to regular stars. Starting generally, stars are classified into 7 main types based on their spectral characteristics, which are related to their temperature and color. These types, in order of decreasing temperature, are O-type stars, B-type stars, A-type stars, F-type stars, G-type stars, including our Sun, K-type stars, M-type stars. These types are based on the Morgan-Keenan spectral classification system, which assigns each star a spectral type based on the characteristics of its spectrum. O-type stars are among the most massive and luminous stars in the universe, with masses more than 15 times that of the Sun and luminosities up to 1,000,000 times greater than the Sun. They are also very rare, accounting for less than 1% of all stars. B-type stars are still very hot and luminous, with masses between 2 and 16 times that of the Sun and luminosities up to 25,000 times greater than the Sun. They are more common than O-type stars, accounting for around 1 in 50 stars in the Milky Way galaxy. A-type stars appear bluish-white in color. They are typically about 1.5 to 2 times the mass of the Sun and are relatively young, with a lifespan of a few billion years. A-type stars emit a significant amount of ultraviolet radiation and have strong hydrogen lines in their spectra. F-type stars are slightly cooler and less massive than A-type stars. Their spectra are characterized by strong lines of neutral and singly ionized metals, such as calcium and iron. F-type stars are sometimes divided into 2 categories: yellow-white stars, F3, F5, and white stars, F6, F9, based on their visual appearance. G-type stars are similar in size and temperature to the Sun and are also known as yellow dwarf stars. Their spectra are characterized by strong lines of neutral metals, such as calcium and iron, as well as some lines of ionized metals. G-type stars, like the Sun, are of particular interest to astronomers because they are thought to be the most likely to host habitable planets. K-type stars are cooler and less massive than G-type stars, with their spectra are characterized by strong lines of neutral metals, such as iron and calcium, and some molecular absorption bands, particularly those of carbon compounds. K-type stars are generally smaller and dimmer than the Sun, and are often referred to as orange dwarf stars. They are also of interest to astronomers in the search for habitable planets, as they are cooler and have longer lifetimes than the Sun, which may give any planets around them more time to develop life. M-type stars are the most common type of star in the Milky Way, and are the coolest and least massive of all main sequence stars, with surface temperatures between 2,400 to 3,700 Kelvin. Their spectra are characterized by strong molecular absorption bands, particularly those of titanium oxide and vanadium oxide, as well as lines of neutral metals such as iron and calcium. M-type stars are also known as red dwarfs, and are smaller and dimmer than any other type of main sequence star. They are also more active and can emit flares and other types of radiation that could be harmful to any planets orbiting them. Each of those spectral type is then further divided into subclasses, with 0 being the hottest and 9 being the coolest. Then there are luminosity classes, 0 or Ia plus 4 hypergiants or extremely luminous supergiants, Ia for luminous supergiants, Iab for intermediate-sized luminous supergiants, Ib for less luminous supergiants, 2 for bright giants, 3 for normal giants, 4 for subgiants, V for main sequence stars, dwarfs, SD4, prefix, or 6 subdwarfs, D4, prefix, or 7 white dwarfs. Then there are the peculiarities. These would be included in the nomenclature in the names. There are 31 distinct peculiarities that any star can have. Those were the main sequence stars. All the colors I mentioned before, red, yellow, white, blue, orange, plus giant, all the types of supergiants, hypergiant, subgiant, variable, dwarf and subdwarf. Any of these stars could have any of the peculiarities. There are no green, cyan, indigo, or violet stars. Then there are many types that fit outside those parameters. Wolf-Rayet stars, or W-type stars, are a type of massive star with a high luminosity that exhibits broad emission lines of helium and nitrogen or carbon in its spectrum. WR stars are classified into 3 subtypes: WN, nitrogen-rich, WC, carbon-rich, and WO, oxygen-rich, based on the dominant element in their emission lines. They are characterized by their strong stellar winds, which can blow off significant amounts of mass, up to several solar masses per million years. WR stars are believed to be in a late stage of evolution, having exhausted the hydrogen fuel in their cores and moved on to helium burning. They are therefore very hot and bright, with surface temperatures of 30,000 to 200,000 K and luminosities of 100,000 to several million times that of the Sun. They have relatively short lifetimes, typically only a few 100,000 years before they explode as supernovae. S-star. S-type stars are a type of red giant star with an excess of carbon and sometimes other elements such as barium and zirconium. S-type stars are typically evolved stars that have exhausted the hydrogen in their cores and have begun fusing helium. As they continue to evolve, they undergo thermal pulses which dredge up carbon from the interior of the star and bring it to the surface, causing the star to become carbon-rich. S-type stars are one of the major contributors to the carbon and other heavy element content of the interstellar medium. S-type stars are classified using the S-process index, which measures the strength of the carbon and barium absorption lines in their spectra. S0 stars have weak absorption lines, while S10 stars have strong lines. C-star. C-type stars are a type of carbon star, characterized by their strong absorption bands due to carbon molecules in their atmospheres. They are typically low-mass evolved stars that have exhausted most of their hydrogen fuel and are in the process of fusing helium into carbon. There are several subclasses CR, CN, CJ, CH, CHD based on composition. D-star. Class D stars, commonly known as white dwarfs, are the final stage of evolution for low to intermediate mass stars. They are characterized by their small size, similar to that of a planet, high density, typically around 1 ton per cubic centimeter, and low luminosity. White dwarfs are no longer undergoing nuclear fusion reactions in their cores, but instead are supported by electron degeneracy pressure. The 7 spectral types of white dwarfs are DA, Db, dc, do, dq, dx, and dz, with each letter indicating the composition of the outer layer. White dwarfs are thought to be the most common type of star in the Milky Way galaxy, with estimates ranging from 75% to 97% of all stars being white dwarfs. The spectral types L, T, and Y were introduced specifically for categorizing the infrared spectra of cool stars, which encompasses red dwarfs and brown dwarfs that emit little visible light and are generally dim. L-type stars are a type of low-temperature brown dwarfs. Brown dwarfs are celestial objects that are too small to sustain stable hydrogen fusion reactions in their cores and, as a result, do not shine like normal stars. Some L-type brown dwarfs may also have clouds of dust and other particles in their atmospheres. L-type brown dwarfs are relatively rare and are mainly found in old, cool star clusters. T-type stars are believed to have atmospheres dominated by methane, water vapor, and ammonia, with little or no hydrogen or helium present. Y-type stars are the coolest known stars and have very low masses, ranging from about 5 to 30 times the mass of Jupiter. They have atmospheres rich in molecular hydrogen and helium, as well as other molecules such as methane, water vapor, and ammonia. There are currently two subtypes of Y-type stars, Y0 and Y1, with Y0 stars being slightly hotter and more massive than Y1 stars. Black stars may form when the universe reaches the end of its life cycle and all matter is drawn towards black holes. These objects would have a mass greater than a black hole, but they would not have an event horizon, allowing light and matter to escape. Some physicists have suggested that black stars could explain dark matter. Gravastars, short for gravitational vacuum stars, are another hypothetical object that could replace black holes. Gravastars would have a shell made up of exotic matter that could mimic the gravitational effects of a black hole, but without the singularity that is believed to exist at the center of a black hole. Theoretical models suggest that gravastars could form through the gravitational collapse of matter. Fuzzballs are believed to be collections of strings or other elementary particles held together by gravity that would replace the singularity of a black hole. According to string theory, fuzzballs could be a solution to the black hole information paradox, as they would not have an event horizon and would allow information to escape. Neutron stars are one of the densest and most exotic objects in the universe. They are formed by the gravitational collapse of the core of a massive star during a supernova explosion. Despite having a mass similar to that of the Sun, neutron stars are incredibly small, with a typical radius of only about 10 to 15 kilometers. Neutron stars are composed almost entirely of neutrons, hence the name, which are held together by the strong nuclear force. The intense gravity of the neutron star compresses the neutrons to incredibly high densities, with an estimated density of around 1,018 kilograms per cubic meter, or about 1 billion times the density of ordinary matter. Neutron stars are also incredibly hot, with temperatures of around 1 million Kelvin in their outer layers, but much cooler in their interiors. They also have incredibly strong magnetic fields, with some neutron stars having magnetic fields trillions of times stronger than Earth's. There are several different types of neutron stars. Standard neutron stars, these are the most common type of neutron star, with a typical mass of around 1.4 times that of the Sun and a radius of about 10 kilometers. They are composed mostly of neutrons, with a thin crust of lighter elements and an ultra-dense core. Magnetars, these are a type of neutron star with an extremely powerful magnetic field, up to 1 billion times stronger than that of a typical neutron star. They emit bursts of high-energy radiation and are thought to be responsible for many gamma-ray bursts observed in the universe. There are two known types of magnetars, soft gamma repeaters, SGRs, and anomalous X-ray pulsars, AXPs. SGRs are sources of short bursts of soft gamma rays, as well as longer X-ray and radio emission. SGRs have also been observed to emit giant flares, which are the most energetic events in the universe since the Big Bang. AXPs are similar to SGRs in their properties, but they do not emit the giant flares that SGRs do. Instead, they emit persistent X-ray emission and sporadic bursts of X-rays. Radio pulsars, these are neutron stars that emit beams of radio waves from their magnetic poles. As the neutron star rotates, the radio waves sweep across the sky like a lighthouse beam, causing periodic pulses of radio emission to be observed on Earth. X-ray pulsars emit X-rays instead of radio waves. Millisecond pulsars. These are pulsars that spin extremely rapidly, with periods of less than 10 milliseconds. They are thought to be old pulsars that have been spun up by accreting matter from a companion star. Binary pulsars. These are pulsars that orbit around another star, typically a white dwarf or another neutron star. Quasars, short for quasi-stellar radio sources, are some of the most luminous and distant objects in the universe. They are believed to be powered by supermassive black holes at the centers of galaxies, which are actively accreting matter from their surroundings. Quasars emit tremendous amounts of energy across the electromagnetic spectrum, including visible light, ultraviolet light, X-rays, and radio waves. Quasars come in various types classified based on their spectral features and physical properties. The most common ones are radio-loud quasars, radio-quiet quasars, flat-spectrum radio quasars, broad absorption line (BAL) quasars, and dust-ridden quasars. Radio-loud quasars emit strong radio waves in addition to optical and X-ray emissions, while radio-quiet quasars do not emit strong radio waves but are still luminous in the optical and X-ray regions. Flat-spectrum radio quasars emit radio waves with a flat spectrum, while BAL quasars show broad absorption lines in their spectra, indicating they are surrounded by gas and dust. Dust-ridden quasars are heavily obscured by dust, making them appear redder in color than other quasars. Now the other types. Cepheid variables are pulsating stars that have a regular periodic variation in their brightness, with periods ranging from a few days to several weeks. The period of a Cepheid variable is directly related to its luminosity, allowing astronomers to use them as standard candles to measure distances to other galaxies. RR Lyrae variables are another class of pulsating stars that exhibit periodic variations in their brightness, with periods typically ranging from 0.2 to 1 day. These stars are commonly found in old stellar populations, such as globular clusters and the halo of the Milky Way. T Tauri stars are a class of young, pre-main sequence stars that are still in the process of contracting and reaching their final equilibrium state. T Tauri stars are typically less than 10 million years old, and they are characterized by irregular variability, strong magnetic fields, and intense chromospheric and coronal activity. They are often surrounded by accretion disks and exhibit strong outflows and jets, which can significantly affect the environment around them. Mirror variables are a type of long-period variable star that exhibit regular pulsations in their brightness, with periods ranging from about 80 to 1,000 days. Mirror variables have exhausted the hydrogen in their cores and are undergoing significant changes in their internal structure. As a result, they undergo regular expansions and contractions, causing their brightness to vary over time. Thorne-Zitko objects, TOs, are thought to form when a neutron star is captured by a normal star. TOs are expected to have unusual chemical compositions and spectra, with enrichment in heavy elements such as gold and platinum. They are also expected to be massive and have high luminosities, making them potentially visible with telescopes. Draconis variables are a type of variable star that exhibit irregular variations in their brightness over a period of several days to several weeks. Draconis variables are red giants or supergiants that are undergoing significant changes in their internal structure and are pulsating in a non-radial fashion. This results in variations in their surface temperature and brightness, which cause the irregular variability in their light curves. Cataclysmic variables are a type of binary star system in which a white dwarf star is accreting matter from a companion star, usually a main sequence or red dwarf star. The accretion process can be highly energetic, leading to dramatic and sudden changes in the system's brightness and activity. Cataclysmic variables are characterized by outbursts and eruptions, including nova explosions, dwarf nova eruptions, and other forms of explosive activity. The accretion process also often leads to the formation of an accretion disk around the white dwarf, which can emit strong X-ray and ultraviolet radiation. Flare stars are a type of variable star that exhibit sudden and dramatic increases in their brightness, often by a factor of 10 or more, due to intense magnetic activity on their surfaces. They are usually low-mass, late-type stars. These flares are caused by the rapid reconfiguration of the star's magnetic field, which releases stored energy pattern. Blue stragglers are a type of star that appear to be younger and more massive than other stars in the same region, even though they are located in regions where most of the stars have evolved to a later stage. They are typically found in dense stellar clusters, where they stand out because they are hotter and bluer than other stars of similar age. They are believed to form through a variety of mechanisms, including mergers between two stars, mass transfer in binary systems, and collisions between stars. Population 1, Population 2, and Population 3 are three classifications of stars based on their metallicity, or the abundance of elements heavier than hydrogen and helium in their atmospheres. Population 1 stars are relatively young and metal-rich stars, with a metallicity that is similar to or greater than that of the Sun. They are typically located in the disk of the Milky Way and are believed to have formed from interstellar gas and dust that has been enriched by previous generations of stars. Population 2 stars are older and less metal-rich than Population 1 stars. They are typically found in the halo of the Milky Way, in globular clusters, and in the bulge of the galaxy. They are believed to have formed from gas that had not yet been enriched by previous generations of stars, and are thought to be some of the oldest stars in the galaxy. Population 3 stars, also known as primordial stars, are stars that are believed to have formed in the early universe, before the first generation of stars had produced heavy elements. They have a metallicity of effectively zero, and would have been composed almost entirely of hydrogen and helium. Fu Orionis, Fu Ori, stars are a type of young stellar object that exhibit dramatic outbursts in luminosity, with increases of several magnitudes in a matter of months to years. These outbursts are caused by accretion of material from a circumstellar disk onto the protostar. The outburst phase is followed by a period of quiescence, during which the star returns to its original luminosity. Zero-age main sequence stars are stars that have just begun their hydrogen-burning phase, fusing hydrogen into helium in their cores, and have not yet undergone any significant nuclear evolution. Protostars are the earliest stage in the formation of a star. They are formed from collapsing clouds of gas and dust, primarily composed of hydrogen and helium, that can be several hundred times the mass of the Sun. As the cloud collapses under its own gravity, it becomes denser and hotter, eventually reaching a temperature and density at which nuclear fusion can occur. The process of protostar formation is not well understood, but it is thought to be driven by a combination of gravitational collapse, turbulence, and magnetic fields. As the cloud collapses, it begins to spin faster, forming a disk of material around the central protostar. This disk can eventually give rise to planets and other small bodies. Symbiotic stars are a type of binary star system that consists of a cool red giant star and a hot white dwarf star, which are in a long-term mutual interaction. The red giant is usually losing its outer envelope through strong stellar winds, which are accreted by the white dwarf, leading to the formation of an accretion disk. Methuselah stars are the oldest known stars in the universe, with estimated ages of up to 14 billion years. Metal-poor stars are stars that have a relatively low abundance of elements heavier than helium, known as metals in astrophysical jargon. These elements are produced through nucleosynthesis in the interiors of stars and are dispersed into the interstellar medium through supernova explosions. Thick disk stars are a population of stars in the Milky Way galaxy that are older than the thin disk stars and have a thicker distribution in the vertical direction from the galactic plane. A zombie star is a rare type of star that forms when a star undergoes a type IAX supernova explosion, but its matter is not completely dispersed. Instead, a compact core of the star remains intact, known as a white dwarf. If the white dwarf is in a binary system with another star, it can potentially be revived. This can happen when the white dwarf begins to accrete material from its companion star, which can cause nuclear fusion to reignite in its core. This revived white dwarf is known as a vampire star and can emit significant amounts of radiation. Thank you for watching. There are definitely many more types of stars. Let me know which ones I missed in the comments.